Thank you, Dr. Arunan. So, once again, a warm good morning to all. As Dr. Arunan told, no, this is first session of the colloquium on light matter interaction at nanoscale. I am from Center for Materials for Electronics Technology, CMET, an R&D institution under Ministry of Electronics and IT, Government of India, dedicated to the development of electronic materials. We develop technologies up to the pilot scale and then transfer the technologies to industries or startups for production. Here in CMET, we have a very good plasmonic group concentrating on the development of novel plasmonic materials and devices. And about the colloquium, anyway, I will not take too much time. But how this colloquium got this shape is that we considered the major four aspects of nanophotonics for this colloquium. One is the electron confinement effect of optical properties of matter, that is quantum confinement effect. So as you know, this led to the tunable size dependent properties and leading to a variety of applications like LED and such important devices. Then the second one is light confinement effects in structured dielectrics. Actually, this has led to waveguides and photonic circuitry and all. And the third one is the modified light matter interaction with the confined light waves. This is quantum optics of nanostructures. And there actually the spontaneous emission and scattering of light becomes controllable by engineering photon density of states. So this has led to the concept of photonic crystals. And the last one is electron excitation by confining light matter or light at metal dielectric nanostructures. So this area has been emerging in the field of plasmonics. So plasmonic devices are capable of sub-wavelength light confinement. So then we framed topics based on these four areas, and we are fortunate that we got eminent professors and scientists for giving lectures in these topics. So dear participants, the whole idea is to motivate you towards the excitement of research in this field and also to take up exciting research in this area. Now, the duration of the sessions will be 1 hour followed by a discussion. You can ask questions or drop questions in the chat box. Now, regarding the sessions, I am very happy to tell you that Professor Vijayan is with us for the first session. He is a senior professor at Department of Physics, IIT Madras, a pioneer in the area of photonics. So, a brief, short biography of Professor Vijayan is he has done his early education in Kerala, obtained first few ranks throughout the school and college education, awardee of NCERT NBS scholarship during college education, MSc and PhD from Department of Physics, IIT Madras. Then served as a senior project officer at IIT Madras for 2 years and as lecturer in Pondicherry Central University for 5 years. Joined as assistant professor at IIT Madras in 1993, currently senior professor. His field of interest is photonics, light matter, and light matter interaction. Graded successfully 14 research scholars for PhD and presently grading 3 more. Published over 100 research publications in international journals and presented more than 100 in conferences. And many of them have received Best Paper and Best Presentation awards. Over 100 invited talks in conferences, universities, and educational institutes in India and abroad. And he has been invited to give inaugural lecture in the NCERT Golden Jubilee Lecture Series at New Delhi in 2011. He is involved in active research collaborations with universities abroad and has been visiting professor in Singapore and Germany. Author of a book on nonlinear optics published by John Wiley International, now into second edition. Currently, the president of Tamil Nadu Pondicherry Regional Council of Indian Association of Physics Teachers and honorary fellow of Kerala Academy of Physics Teachers. With this, I welcome Professor Vijayan for delivering his lecture. Sir, please.
Very good morning to all of you. You know that this colloquium is on light matter interaction. So how do we start a colloquium like that? There are very serious lectures by practicing scientists who are actually working in those areas and on different topics. Important frontier topics, very carefully chosen. That's one thing which I appreciate. As you can see from the abstract book, It's actually a rich program with a lot of useful lectures by experts. So we start lightly because it's a light matter interaction. And I thought I will give, my task is to give you an overview of the program. We start with the first point in your syllabus, that is the basics of electrons and photons. And from there, I touch upon different aspects of these new trends and the new frontiers in optics and photonics. So I will introduce several concepts, and those concepts will be detailed later by people working in each one of them specifically. So there might be some overlap, but this is just to give you a preview and a basic understanding before you face a more detailed lecture. So if you find any one of them particularly interesting and any topic of special interest, note down and look at attend carefully the talk by that particular expert and get the details. Let's see. And I have quite a lot of things to say because optics and photonics is a very rich frontier indeed. But I will restrict to 1 hour. There was a famous speaker who wanted to give a talk in some place, and he was supposed to speak for 45 minutes. And after 1.5 hours, he was going very strong still. Then he goes to looks at the organizer and says, "Sir, how much more time can I take?" Then the organizer didn't want to displace the big man. So he said, "Sir, you can take any amount of time, but they will go home at 10 for lunch at 12 o'clock. That's what they said. So with that in view, let us see how we can optimize and manage time. That's the plan of my talk. And this is also the learning objectives. Teachers are familiar with the learning objectives, right? So this will be the learning objective. The learning objective is that you will be able to relate each one of the picture with something in optics and photonics. A deep concept, really deep research level concept, each one of them. I would like to invite all of you to a paradise. Don't immediately you will get scared. What paradise? That is after finishing all those fantastic things that we are doing now. And he is inviting now itself to the paradise. But this paradise is different. This paradise is made up of very interesting phenomena of optics. But I have listed only a few of them here for obvious reasons. But there is a rich plethora of processes in various frontiers. So that way, you may wonder, optics, is it a dull subject or is it a new fantastic subject with emerging frontiers? That is the question which will be there in your mind, optics and light matter interaction. Is it really an interesting topic with a lot of potential, or is it just a textbook, a boring textbook topic? This is what you will answer yourself at the end of this whole program, all these lectures and program. You will also get partially, you will be getting some answer by the time I complete, because it is an overview. So that is the first point I want to make. Optics is a paradise of interesting phenomena. Interesting from the basic point of view, and there is a scope for a lot of scope for application potential. That is what we are talking about light matter interaction. It's actually very nice to see this light matter interaction. What are important here? The concepts. If you want to do research in this field, be thorough with the concepts. Concepts are electromagnetic theory and quantum mechanics to start, basically. So these two topics are very important. If you have any interest in these topics, go back to the basics and be thorough in both these. Then your life will be really colorful. Now, light matter interaction has many things. Concepts is the starting point, and then there is material, different materials. That is where matter comes in. What kind of materials? And can each material give an interesting phenomenon or application or basic interest? That's the question. That we know. Concepts are important, materials are important. But something which some of you may not know yet is structure is also important. Not only matter, but the way it is structured is also important. So now you will, maybe this is a new thing to many people. So you think, oh, structure is very important. But at the end of the program, we will also tell you that lack of structure is also very important. Not only structure is important, but lack of structure is also very important. That is actually my research area, but somebody else will be talking about that later. Okay. Now, what are the kinds of light matter interaction? It is not very scarily complicated. As I was telling, this first talk is purposefully kept light and it will be an overview. So what are the different modes? It is not difficult. What are the modes of interaction? First, ordinary light interacts with ordinary matter. That is how we can see all the world around us, because ordinary light interacts with ordinary matter. The usual phenomena which I listed there, all of them come under that. If you think that someone looks very beautiful or handsome or something like that, and you are losing your peace of mind, just think that it is just ordinary light interacting with ordinary matter, nothing more than that. It's a light matter interaction at the crudest level. We graduate to the next level. What is the next level? Extraordinary light interacting with ordinary matter. Extraordinary light? What is extraordinary light? Extraordinary light, there are examples. You can consider lasers as extraordinary light. Okay? So lasers, extraordinary light. When that interacts with matter, there are new things coming up, which were not there in the first part of the light matter interaction. That is one example of extraordinary light. But of late, there is another kind of light, extraordinary light, which has become very important. That some of you might have heard of it, and that is the structured light. We are talking about structured matter, but there is structured light also. Light with angular momentum, vortex, light with vortices. That means it is not a uniform cross-section across the beam, not even a Gaussian cross-section as usually there in most of the lasers, but a structured kind of Legure Gaussian and things like that. A structured, for example, center can be a dark one, ring kind of thing. That just is the simplest example of a non-Gaussian or non-uniform light. So that kind of beams are becoming very important in recent times. You can do a lot of wonders with that kind of beams. So that is another aspect of light matter interaction. So my point here is ordinary light interacts in some way, and most of it is already discovered, and a lot of applications are also there. But these kinds of extraordinary forms of light also can interact with matter and create a lot of wonders. What is the third one? Ordinary light interacting with extraordinary matter. What is extraordinary matter? All of us think that, oh, I am an extraordinary matter. No, you're all ordinary matter only. What is this extraordinary matter? What are examples of extraordinary matter? That you will start seeing immediately after this lecture. For example, nanostructures. Nanostructures, semiconductors, various kinds of, especially nanostructures which are rather new. We think it is new, but the engineer with a capital E has already discovered it and used it in nature. But we think it is a new thing and all that. But anyway, so that's a special matter. Let us call it as a special matter, that kind of matter. Structured matter, that is another kind of special matter. So I'm talking about ordinary light interacting with extraordinary matter, such as nano, structured, unstructured, different kinds of matter. And then what you get out of it. That is another aspect of it. So what is the last aspect? Only 4 aspects. Now you can guess what I'm going to say next. Extraordinary light interacting with extraordinary matter. That is research. That is where research is going on. All the easy things people have already done. The new researchers have to do difficult things. We have to explore what extraordinary light does to extraordinary matter. You heard of spring doing something to the cherry trees and all that. Extraordinary light interacts with extraordinary matter. So that is the kind of research frontier. And all these talks which are going to follow are examples of that. And I will introduce you to at least some of them in this talk. First aspect that we look at is the basics, of course. From optics to photonics, the journey from optics to photonics. What is light actually? Is it a particle? Is it a wave? Is it a quantum? What is it? That's the first question that we ask. We start with Newton. We say, we have to think in the beginning when you start something. So when you talk of light or when you talk of physics, the name of Newton eventually anyway comes up there. Though the Apple story, you may think that why am I talking about the Apple story? Apple story is not related to optics. Apple story is related to gravitation. But then let us see. Look at the second picture. The first picture is before the apple fell, and the second picture is after the apple fell. And if you look at it closely, I have modified that picture, and I have put some objects there. What are those objects? They are the Newton's rings. So that rings a bell. Why this picture? That is talking about, okay, if Newton were really a genius, the point here is, if Newton were a better genius, he's already top genius. If he was better than the best, then he could have looked at the wave theory rather than the particle theory. I will elaborate on that later. But if he were top than the best of the best, if he were that level genius, he would have taken enough precautions to avert some of the mishaps. But that mishaps became a very great thing in physics. Luckily, he did not do that when he was reading. So the basic confusion when we talk about electrons and photons, are these objects particles or waves? Does it have two forms, or is it only the same thing? Particle is very different from a wave. Particle, you can just bombard something with it. The interaction of light matter interaction with particles, if light is a particle, is very different from the interaction. You look at a wave, or look at a rock on the seashore. There are two ways of blasting the rock. One, put a bomb on it. Then there is some instantly that will be gone. That is particle. The other one is the waves keep on interacting with the salt rock, and over several hundreds of years, slowly that rock disappears into the sea by some chemical equilibrium and all that. That can happen. That is the wave interaction. So first point, the next point is light matter interaction is very different if light is a particle or if light is a wave. So there is a lot of confusion for scientists. As I said, you will see some Malayalam writing. If you can't read it, read the meaning which is given at the bracket, in the bracket. Now, I think after looking at my picture for a few minutes, you would have realized whether light is actually a wave or a particle. But the issue is actually very complicated. The question is this: if you want to explain Compton effect to someone, you want to understand, or you want to understand what is happening in Compton effect, the conservation of momentum, conservation of energy. So when you say conservation of momentum and all that, you are thinking of particles. You are talking in the language of particles. Particles bombarding with each other, electron bombarding with photon. That is the picture with which you can explain Compton effect, or the rectilinear propagation of light. So in that, you need the particle picture of light. On the other hand, things like interference, polarization, diffraction, which also we see in daily life, that can be explained only with a wave picture of light. So finally, what is it? So it depends on which experiment you are doing. If you are doing Compton effects, both electron and the photon behave like particles. And if you are doing a diffraction experiment, there, of course, if you are doing an optical diffraction, then the photon behaves like a wave. And if you are doing electron diffraction, electron behaves. You know that J.K. Thomson received the Nobel Prize for discovering the particle called electron. After 30 years, his son G.P. Thomson also got the Nobel Prize. For what? The famous Thomson's experiment, where electron diffraction, they showed that electron gets diffracted. So he showed that his father got Nobel Prize for telling it is a particle, proving scientifically, experimentally that electron is a particle. And G.P. Thomson got the Nobel Prize, shared the Nobel Prize with other scientists for proving that electron is a wave. Electron can interact with matter, diffraction of electron. That is what the famous experiment which he did. So the students have a confusion. Students, don't worry. You go to the lab, your first experiment is Compton effect, light and electron both behave like particles. Next day you go to the second experiment, that is diffraction, it behaves like a wave. So you are happy. But the intelligent smart student had a doubt. Sir, what happens when you are not doing the experiment? What is it? Is it a particle or is it a wave? when you are not doing the experiment? That's really an interesting question. Maybe it is a superposition of both. And when you project it onto something, it just becomes meaningful. The Copenhagen interpretation is like that. So this point is very... So what the teacher answers is, when you are not doing an experiment, you cannot talk about it. Physics is basically an experimental science. So you can only say, is it a particle or is it a wave when you are doing an experiment? It's like a coin. You throw a coin. What is its state? Is it plus or minus? Is it heads or tails? It can be a combination of both. Finally, when you catch it, you put to one state particularly, then it becomes heads or tails. So the live cat and a dead cat kind of thing happens here. Of course, this concept is very important nowadays. People thought it's maybe a useless fancy. No, it is used in quantum optics these days, a field which is coming up in a big way. Now I will give you the story which I told just now is from a novel called Mr. Tompkins in Wonderland by George Gamow. Those who have not read it, please read it. It is there even internet, I suppose. It is those days when I bought it, it was something like 10 or 20 rupees from a second-hand bookshop. It may be there in your library. Otherwise, you ask your college teachers to buy it in the library, or you can buy it. I don't know recently I have not searched for it. So this is a big paragraph. You should not write big paragraphs in your PowerPoints. So I will just tell you what is written there. What is written there is basically what I said. When I do this experiment, light behaves like a particle. And when I do that experiment, it behaves like a wave. So what is it when I'm not doing an experiment? So he says, your question has no physical sense when you are not doing the experiment. So that is where the particle wave controversy stands. But what is the resolution of this? If you can call it as a resolution, that is given by our great man. Quantum mechanics is a description of the behavior of matter and light in all its details, and in particular, happenings at an atomic scale. Things on a very small scale behave like nothing that you know in the other ordinary life. So it's scale. It's a scale of that. We are familiar with whatever, our size, meter, a few meters. That's what we are familiar with. But when we go to the world where you are talking about electrons and photons, then you can't have analogies with common normal thing. Like once when our director was inaugurating a conference on on nanotechnology, he was inaugurating this thing on nano science or nanotechnology. And he happened to be from the ocean engineering. So he said, I don't know how you people are doing research. For me, it is very nice ship. I can see the ship. I can go to the ship. But you are working with the nanoparticles, and you can't even see that unless you have very costly crores of rupees. So I think my research is more comfortable than your research. But light matter research is all about how the photon and electron behaves and interacts at that level. They do not behave like waves. They do not behave like particles. They do not behave like clouds or billiard balls or waves on springs, like anything what you have ever seen. So if you want to understand it, you have to learn their language. And their language is a Schrodinger's equation. If you are good in matrices, go for the matrix mechanics. If you are good with the differential equations, go with the Schrodinger equation. If you are not good in the matrices and Schrodinger equation, leave physics and go. That's what you have to do. So that is the message of Feynman. You have to talk. How do you talk to a baby? You have to talk in the language of the baby, right? Not in our language. So we have a language problem. It's light and photon come from another continent and color our days. So that's what Feynman says. And Feynman is really, for all physicists, Feynman is someone who you should read. You should read this book. You Are Surely Joking, Mr. Feynman. There is a book called You Are Surely Joking, Mr. Feynman. And that is a must read for all physics students, whether you like light or matter or the light doesn't matter or whatever it is. You should read that. And that will really inspire you. Every page of it will inspire you. It's a fantastic book. Take it from me. It's a fantastic book. You will not. One caution: don't read it when you have an exam, because then you will not read the topics for the exam. Read it only in vacation, or that's only one warning, statutory warning which comes with that book. You must be surely joking, Mr. Feynman. Again, it is a book which is not very costly. You can buy, or you can ask your college or parents to buy it for you. Feynman gives another interesting lecture, not in the famous Feynman lectures, but another lecture he gave in Mexico for BSc students, somewhere in North America for BSc students. There he talks about this. Take the simplest experiment in optics. What is the simplest experiment in optics? You will agree with me after 2 minutes that it is the most complicated experiment. The simplest experiment is take a glass, piece of a block of glass, send light to it. What happens? Some light is reflected, some light passes through. The mystery starts there. The mystery starts there. And people measured what percentage of it is, something like 4 to 16%, which comes out of the glass. The rest goes in. And if you don't have anti-reflection coating, that's what you get, something like 4%, 5% less of light. Now the mystery is here. The light, electron, photon mystery is here. Consider the army of photons marching to the glass. Who decides how many will go? Which photon will go this way? Which photon will go this way? Just think of it. It's a mystery. The simplest experiment which you thought is becoming very complicated. Not only that, they found that this percentage of reflected photons depends on the thickness of the glass. It becomes really mysterious. What happens to the captain? The captain of photons, they are marching to the glass. So the captain has first to decide who will go this way and who will go this way. Not only that, before traveling, he has to go with a tape and measure the thickness of the glass and then decide, okay, 10 of you go this way. He gets the captain of photons really gets exasperated, and he says, okay, half of you go to the left side, half of you go to the right side, the remaining people come behind me. That's what he will say. So you get the point. And okay, you can do that. You can go and measure the thickness and then decide who will go this way, who will go that way, who's on medical leave, somebody will substitute. But this has to be done at the speed of light. This has to be done at the speed of light. That's where the mystery is. So that is one of the one frontier which I am introducing and leaving at that. If you want to read more on it, you have to read the fantastic book, another fantastic book by Feynman, The Wonderful Story of Photons and Electrons. It's a popular book with subtitle QED, The Wonderful Story of Electrons and that was the book. This is the second book I am suggesting. Please note down somewhere. I am giving you a lot of take home. Don't say at the end of the lecture, I didn't get any take home from this lecture or something like that. Okay. And the first one was Gamo's book on Mr. Tompkins in Wonderland. Okay. If I think, yeah, I will leave it that and go to the next one. My problem is to what depth each one I have to go, or then I will not be able to cover the overview of everything, but doesn't matter. Whatever we can do in the reasonable time, we will do. So it's like, there was an army camp. The army camp started with an announcement. First, the major will address you and tell about some of the general problems. And then the general will address you and talk about some of the major problems. So that's what is going on right now. So we have to have a balance of general and major. So the talks on major issues will, I think this topic is probably also included. Now, one important milestone in light-matter interaction, another important milestone in light-matter interaction is the creation of lasers. God said, let there be light. But Einstein was not happy. Einstein didn't say much. Einstein just did A and B. And then you had lasers. What is this A and B? Should I ask some participants to tell me? What did Einstein say? The beginnings of quantum optics. Time-independent perturbation comes in there. What is A and what is B? Okay, no volunteer. I think this audience is still have not woken up fully. Okay, let's see.
Energy and momentum.
Huh? Energy momentum?
Energy and momentum. It's Einstein's
in the
coefficient.
first of lasers.
Spontaneous and stimulated emission.
Einstein's coefficient, there are famous Einstein's coefficients of different kinds of emission, stimulated emission and spontaneous emission, things like that. And that led to a lot of new areas in optics. I'm just touching upon that because it is an important thing which you cannot ignore when you talk about light matter interaction. And what are the important concepts involved in it? What did Einstein do? What is the genius of Einstein? Who discovered the laser? Einstein or C.K. and Patel or who discovered? The question is this. Cavity was well known. In World War and all that, people were using cavities, the microwave cavity. Cavity concept was well known at that time. Black body emission was also well known independently. When the lasers, I think around 1960, when it came out, people knew about cavities, people knew about the black body emission, but the genius of Einstein put the emitter in a field, put the black body in a cavity, put the emitter in a field, and then see what happens. That is where the genius happened, and that is where stimulated emission happened. And you got a fantastic light, fantastic light. The important concepts are of stimulated emission and the gravity physics, then why population inversion is required. And nowadays, the most important thing, you get ultra intense, ultra short pulses, just a few optical cycles. And with that, you explore more. You explore more, especially chemical reaction. For example, some enzymes, some catalyst. What is the catalyst doing? A plus B plus C giving A, B plus C. So catalyst is not doing anything. But you do an ultra fast reaction. And with the probe it. It is doing something. Only you don't see it. So if you see at that scale, ultra fast scale, then you see more of what more wonders are revealed before you. So that is what this is an important aspect of light matter interaction. Let us go to the secrets of color. I will go through this quickly because this is easy and you may be knowing most of the concepts related to this. The color, the secrets of color around us. We all like to live in this world mainly because it has got wonderful colors in it. So what do you do in your vacation? You go to some nice beach or something and enjoy life, right? Getting away from it all, spending quality time with our family. What a beautiful moment. The whole family is happy. The scientists, that weird fellow is a scientist. And what is he thinking about? He's not thinking about the blue sky or what. He's thinking of scattering, optical light matter interaction. That is what will happen to you after listening to this lecture. You will spoil your vacation and you will spoil your okay, you will be now thinking only of light matter interaction. Apple's secrets are finally revealed. What are the secrets of Apple? Not the amount of money they have put in Apple and all that. Why is it Apple red? Because, as I said, these are easy concepts you can understand very easily. Scattering occurs all around us. And that is why. Absorption, scattering, and all that. So these are the standard fundamental things which you learn first: absorption and scattering of light. And you know all that. But what is something which we often forget is what happens between the cup and the lip. What you have here, the light that you have here is not what the light which is coming on. Something happens in between. A lot of things happen in between. A lot of different particles there and all that. And because of that, we evolve. Suppose it is made in some way and we keep on putting some pollutants into the atmosphere, then what will happen? Then pollutants will go and sit there and then the spectrum will be different. Some of the infrared, the microwave will be more or less like that. So what you get, the spectrum what you get is with air in the atmosphere and the other things in the other spheres. If you pollute it, if you put more and more chemicals there and pollute it, the spectrum will change. Then what will happen to human beings? We will evolve. So your grandchildren's grandchildren will have big eyes and antennas and all that. So that is what will happen if you pollute The point to understand is our eyes are designed for what light comes out. Not only what light comes out of the sun, but what we get finally. That's the importance of scattering. Okay. So you should not tell somebody if you like the eyes of somebody, don't say your eyes look beautiful. You should say your optical detectors are optimally designed. That is what is more important in the context of light matter interaction. So there is a lot of things which happens between the cup and the lip, and what you see is a result of all that. After all that light matter interaction, what you get is available for light and your interaction. Why should you listen to this lecture? Most of the students attending here will have this problem after 10 years. If you're finding it difficult to read, the boy asks his father, what are clouds made of? He says, I used to know that. I think it is mostly water. Then how do they float? Well, it's sort of evaporated water. Maybe there are some other gases. I'm not sure. So this is what the father says. And the son says, so why are they white and the rest of the sky is blue? Heck, it beats me. I guess we ought to look up this stuff. So he says, there is no qualifying exam to be the dad. Be a dad. So now you can tell him, oh, I have undergone a course in light matter interaction. So I know many things which I can explain nicely. So that's why you should listen to this lecture. So this is the most famous elephant of Kerala. My point is, what do you see? How do we see what we see? And how do we see what we don't see? That is the question which we are asking. There are methods to see what we don't see. So what is this? Which is the beautiful elephant, left or right? But the point is, this is a false colored image. What I'm showing you is an infrared image. It is a false color image. We can't see red and green. It's painted differently. I mean, not painted. The color coded. The hotter regions are coded with. That's what you normally do in the research simulations. The hotter regions are but how do you get this information? Hot or cold information? That is by the infrared photography. So that is what you see now. And that gives you quite a lot of other information. For example, people were wondering, zoologists did not know why the ear, elephant's ear is so big and it always does this. The answer is now known from this infrared research. It is because the elephant is a huge machine. We are all huge machines. And we generate a lot of heat. And elephant being very huge, it generates quite a lot of heat. So it needs to cool itself. But we thought so far that it is enjoying the music in the festival. No, it is doing its biological function of light matter interaction. This is not light matter interaction. Only we understand it through light matter interaction. So this is important. This is not a new kind of yoga proposed by the Prime Minister. It is it's actually again an infrared image showing the temperature distribution. So this is the information you get if you look at different aspects of electromagnetic. There is a spelling which is electromagnetic spectrum. Each part of the spectrum gives you different kinds of information. It is like you are in a dark room and you want to see what is in the outside world. You open one window and you see something. You open this side of the window, you will see something else. This side the road traffic, that side forest. So you open each window, visible, ultraviolet, infrared, and then you get different information from that. So that is the basis of spectroscopy. So each one is important. And the principles are the same for all. Electromagnetics is the same. Only the scaling and other issues, absorption, those things matter. So this is important. And this tells you about some aspects of thing which you cannot see with other wavelength. Looking at objects, looking at matter through different aspects of electromagnetic wave, different wavelengths of electromagnetic waves, gives you different kind of information. When you have trouble, you go and take X-ray. So that you can always say. So I used to tell my audience that I am as handsome as Mohanlal, but so far no audience has agreed. I don't think this audience will also agree. But I'm not unhappy because it is not my fault. It is the fault you are looking through visible light. That's the problem. You look through X-rays, I don't have a bent to one side at least. So if you look at through X-rays, you may agree that So it all depends on what wavelength. So when you look for, again, you people are at the right age, within 10 years, we'll be looking for, students will grow up and they'll be looking for proposals and all that. So don't ask for Facebook photos. Ask for X-rays, and because face is important, yeah. Up to the age of 20, 30, your face and all those things are very important. But between the life 40 to 80, your thyroid and your pancreas becomes more important in life. So probably you should ask for X-ray pictures and infrared pictures and all that, so that you get all this. So my point is, you look through different wavelengths and you are seeing different kinds of information. That is where it is beyond spectroscopy. Spectroscopy at all electromagnetic wavelengths. Okay, now I have only a few mention only of the topics which are going to come up. Color. Let's talk about color first before going to nano. Let's talk about color. Color. Why is this color? Why this particular color? That has generated quite a lot of physics. Again, my next take home. You should search for why the sky is blue. A talk, radio talk for students given by C.V. Raman. The talk is not available, the text is available. Audio, video are not available, the text is available, you can easily get it. Actually, someone has published, I think somebody published a book on it, but unfortunately the book has more pictures and less text. You should so if you can't get the real full text, you can send me an email, I will be able to send it to you. So this color, there's a lot of physics in this. It's not the sky alone. Then it is not a big deal for light matter interaction here. That is connected to molecules. Molecules of matter, the dance of molecules, all that is what determines the color and scattering. That's what Raman discovered. So it goes to the heart of matter. The molecules, the atoms, the clusters, the bonds, various things. So that is the significance of Raman's discovery. Color, is it a physics concept or chemistry concept or a biology concept? Some examples are already there in the picture. The simplest way to understand that color need not arise from chemistry is the rainbow. It's not because of the chemistry of water. The rainbow colors do not come because of the chemistry of water. Let us answer this question. What is meant by chemical color? The shirt you wear and all that. That color is pigment, dye, pigment, chemical, because of some chemical. Fortunately, that doesn't change. Suppose I wear always a red shirt, and suddenly one day I start wearing the green shirt. Then there will be political significance and all that. So luckily that doesn't happen. That color doesn't change like that. But if you put oil on water, that color changes. You see colors, and that color changes. You see evolving colors and all that as the oil spreads on water. You know why it is. It is not of chemical origin, it's of physical origin. So my point is that the color can be of different origin. Color can be due to plasmonics. That is one of the topics which you will be hearing later. Plasmonics talks about the oscillation of electrons with the background positive charge in the rest of the crystal. So that oscillation can resonate with the light wave, and that is how you get plasmonics. Plasmonics is fine, but there are some evil effects of plasmonics. The color of gold is because of plasmonics, and that has led to a lot of issues, this color of gold, and it has spoiled many lives. The greed for color, greed for gold, that is an evil, that has become a social evil, and people are getting, even the state government is getting aware of this kind of gold issues and all that. Why in weddings and all that, the people ask for gold and things like that. So now, hopefully, some legal thing will be to eliminate the evil effect of plasmas. Another color, another kind of color. And what is this color? This is a beautiful, wonderful color. You can see it in many churches in Europe and all that. This color is due to glass. Actually, basically, glass is a silicate, mixture of silicate to sodium and potassium. But in that, if you put in some other material like semiconductors and make ions of semiconductors in a portion of an insulator, Then you get nice things called quantum dots. That is another topic you will hear in more detail later. And that can change the optical properties, all properties of matter. And you will have at least 1 or 2 lectures related to that kind of optics. Light matter interaction in the nano form, especially. To start with, the physical aspect of color becomes more important. And the color will depend upon the size of the particle. That story will come out. This is the famous Notre Dame, church in Notre Dame, and there you will see various pictures and all that. That's all using the doped glasses. The secret of color here is, while making the sodium silicate, making glass, sodium silicate and potassium silicate, you mix some semiconductors and you create a semiconductor island in an ocean of insulator. That's the basic. More will be given by the respective speakers later. C.V. Raman, again I mentioned Raman. Raman was very much interested in the color and sound both, and color of various objects. This is a buried secret of color. And this also is related to nano intuitions. All these wonderful colors of natural objects like this are because of nano intuitions. So this one more point about plasmonics. Plasmonics is related to the color of metal. Why the gold? The color of gold is different from color of silver, and color of silver is different from color of copper and color of platinum. Suppose somebody comes and sings to you, Na chahu sona chandi, na mangu hira moti, don't fall for it. He is going to ask for platinum. Be careful. He is going to ask for platinum. So that is not enough. So all this is related to plasmonics. All this is related to plasmonics, which will be another topic. What is the secret of beauty? Let us spend a few minutes on the secret of beauty. If I ask what is the most beautiful object in the world, people will say what I see in the mirror every day. Everyone will say that. Oh, what I see in the mirror, that's the most beautiful. What is the next most beautiful thing in the world? People say Mona Lisa. Many people say Mona Lisa. So what is the secret of Mona Lisa? What is the light matter interaction happening here? People did research on it. People did research work on it and found that it is because of the artist's secret technique. Ultra thin layers of paint in glaze. So what is important here is ultra thin layers. How thin? Ultra thin, of the order of the wavelength. Layers of what? Different refractive index. And that gives you structured matter. In particular, this kind of structure is called a photonic crystal. So you will have one lecture on that, photonic crystal, their basic physics and their applications. Again, we talked about this, the nature, color in nature. What has this to do with photonic crystals? Here again, it is not a biological color or chemical color, or all is used. All kinds of coloring techniques are used. And what do you have here? If you look at it, you have structures at millimeter level, centimeter level, nanometer level, micron level. That is what you see if you look through a microscope. And at each level, you have diffraction and interference happening. And that is what gives you the color. For example, the butterfly. The butterfly's color is also due to that. The wonderful structure. These are all structural colors. These are called structural colors. And that is why I said in the beginning, structure is also important. So the physics of it will be given in a different talk, where they will talk about the photonic crystals. If you look through, if you look at a wing of a butterfly, yeah, this is the wing of a butterfly, and everybody will agree that this is a beautiful object. If I zoom one point, I get something like that. If I zoom one point of that, I get something like this. If I zoom one point in an appropriate microscope, I get like this. So what everybody agreed as beautiful here, now you will say it is not agreed beautiful, it is ugly. So what is beautiful and what is ugly? It depends upon what? Your eye of the beholder? No, beauty does not depend upon the eye of the beholder, but it depends on the eyepiece of the microscope that you are using. So that is a new definition of it. So this is about structured matter, and as I said, there will be another talk which will talk about which will give you details, the physics of structured matter, in particular photonic crystals. It actually happened in 1987. Two people asked two different questions. Yablonovich is an engineer in Canada. He asked a question, how can I inhibit spontaneous emission and get a better laser, more efficient laser? An engineering question. How can I make a laser better? And Sajeev John, who is of Indian origin but in Canada now, he asked a question, can I localize photons just like the Anderson localization of electrons? That is a basic physics question. So the two different questions, very different questions, but the answers turned out to be the same. Answer turns out that it is a photonic crystal which does both this. With that, I will go away from photonic crystal, but the story doesn't really end there. All around us, if you look at it, lot of interesting things are happening all around us. And this play of colors, a lot of it is not only structured matter, but also unstructured matter, which gives wonderful colors, changing colors and all that. So light matter interaction is quite everywhere and quite deep. The final topic I am going to talk about in the next few minutes, I started I think 10 minutes late, so I can take a few minutes more, is about a new kind of material. See, when I talk about refractive index, you know how to get refractive index. How do you get refractive index? Okay. So there are two different things. Light is an electromagnetic wave. But when I say electric phenomena, you think of getting a shock or things like that, right? Or a paper thing on a comb, paper jumping to a comb. That's the picture which you get when you say electric. When you say magnetic, it's a totally different picture. You think of various things being lifted by magnets and all that. All electric phenomena are governed by the epsilon. What is epsilon? The permittivity. Epsilon naught is the permittivity of. And if I ask you what is the value of epsilon naught, most of you may not remember. What are the dimensions, units? That also you may not remember. Okay, that's okay. You can always look up. So that is a complicated quantity, and which governs all the electrical phenomena. What about magnetism? All magnetic phenomena are governed by the permeability. Again, what is the value of it? What is the units of? What are the units of it? Are complicated questions. Okay. Now you do a trick. Multiply this together. Let's go to free space. Take epsilon naught and mu naught. Multiply them together. Take the square root, and then divide by. Find the invert it. Then you can't have an excuse. You must know that number. You must know those units. What are they? 1 by square root of epsilon naught mu naught. There's a number.
1 by C.
Yeah, that's it. If you invert it, you can see. See how it comes from two different things, electric and magnetic phenomena. And what you get is light out of it. Okay, why am I talking about it? You may think that I'm talking about the origin of light at the end of the lecture. No, I'm talking about a particular aspect of it. You have 25, square root of 25. You want to take square root of 25. The answer is 5. Everybody knows. But mathematician will say minus 5 also is an answer. There is a wonderful book called Leelavati. You all have heard about it. It is a mathematics books written in Sanskrit, but English versions are available. So there, the problems are very interesting, like a story. Each problem is like a story. So quadratic equations are there in that. And finally, you have to find it. Arjuna was in war and so many arrows came to him. He put so many arrows to other people. And finally, the question is how many arrows were there in the beginning? So you have to assume X and all that. And finally, you will find out. So in that famous shloka on Arjuna's arrows, it's a quadratic equation. Some detail, we are not interested in those details. But finally, the answer will be minus square root of 25. Answer will be square root of 25. So the answer is 5 arrows. That is what Arjuna had originally. But minus 5, we just forget, neglect, you don't look at it. What do you mean by 5 arrows? What do you mean by minus 5 arrows? Is it that somebody put 5 arrows on Arjuna? No, that is unthinkable. Immediately there will be a nationwide calamity if I say Arjuna was hit by others. No, I'm not saying that. Now let us look at epsilon naught. We are talking about light matter interaction. So let us talk about epsilon and mu. You multiply this and then you get to take the ratio of epsilon naught mu naught by epsilon mu of the material. Then you get the refractive index of the material, right? But what is epsilon? Suppose epsilon is negative. Suppose you make a material with epsilon negative. Don't worry whether we can make. We'll worry about it later. Then you make a material with mu negative. And then you multiply together, you will again get plus. Again, you will get a positive. But somebody discovered, let's go to the story. Yeah. The person called, scientist called Bisilago said, in that case, you have to take the negative root. It will have a significance. So that was proposed by Victor Bisilago. And John Pendry is the one who has made maximum contributions in recent times on it. And you can look at their names, search their names, and you will see enough material on that. This, I think there is no lecture on this. Maybe some passing mention will be done in the due course. So I will go a little bit, a few minutes more on this. The starting point is this. The square root of epsilon and mu for a material, epsilon r and mu r, will give you the refractive index. But if both these are negative, still you should get the same refractive index. -1 into -1 is +1. But Bisilago said and Pendry proved that in that case, that kind of extraordinary materials, you will have to take the negative root. It makes sense. How does refractive index make a sense? Where does light go? Light goes into the glass, and then where does it go? This way or this way? That is where this becomes important. So light goes in the wrong way if you were to consider a material with that kind of structure. That is what is proved experimentally, proposed and proved experimentally. Let us look at the material, all materials in the world. So you have a picture here. Okay, I forgot that question will come here. What happens if one of them is negative? Epsilon and mu. We have two things, epsilon and relative permittivity and permeability. Suppose both are positive. Let's first look at both are positive. Both are positive, you get the transparent media. No problem. The usual optics, all non-optics. What happens if one of them? If one of them is there, then there is it becomes imaginary. It becomes imaginary means light cannot propagate. So light propagation, it becomes instead of a sine wave, it will decay. That's what happens. So this opaque, either epsilon becomes negative or mu becomes negative. In both cases, you have opaque materials. So we are not interested in that. The last one is epsilon is negative, mu is also negative. And then you get wonderful things. Then you get the negative, the so-called negative refractive material. For those materials, we have to consider the refractive index as negative. And that, how do you get it? Here I have mentioned some of the materials. This table is just to tell you that it is very difficult to get mu negative. In nature, such things are not there, rarely there. Materials with mu negative. What do we want? We want to see the fantastic properties of negative refraction. For that, we need a material for which epsilon is negative, mu is negative. But the table tells you that mu negative is not easily available. But epsilon negative is available. You are all familiar with this kind of pictures, where some frequency ranges you have negative value of refractive and a negative value of epsilon r. So you have to make artificial materials. And you make these artificial materials, and then you get then it is connected to plasmonic. You have the plasmonic frequency coming in a big way, and that will be talked about in a different lecture. I think 1 or 2 lectures will mention the aspects of plasmonics, though not probably in metamaterials. Probably that also will be included, but plasmonics will definitely come in as a topic. So it is possible. What I want to convey here is that it is actually possible to have epsilon negative easily, but mu negative is not possible. Possible easily, but you can make artificial, as I said, light and extraordinary materials where that is possible. If you make such a material, the refraction happens like this. That is an interesting aspect of negative refraction. And this picture shows what will happen if this thing, whatever you see in violet color, is negative refractive. If you make an artificial material. But this picture is not a true picture. It will not happen ever. Because you cannot have a uniform liquid or something with negative refraction. All you have is a structure. As I said, you need to make an extraordinary material for the mu part being negative. So what you will see actually is not this kind of material, but this kind of material, but this kind of structure where you can have all that. What are the applications? You can do super imaging, super lens, without any ray getting lost. This is ordinary lens, kind of refraction, and here, and you don't need a curvature for the lens. Without curvature, you can make a lens. So these are the kind of things you get if you have this kind of materials. This is the normal and this is the super. In particular, the higher, all the frequency, all the spatial frequency, information is divided in, distributed in various spatial frequencies. And in this kind of imaging, using plasmonics, evanescent wave, and metamaterial, you can actually get the entire information. And you can make things invisible. What is the idea here? Basic idea? Manipulate the directions of light rays by putting appropriate materials. This is called clocking. You can read that reference where it is written. So by which you can make things, this is called clocking. But don't think that you can go with a red color shirt and do all nonsense and then you will not be caught. What happens is, because it's only one wavelength. It's only one wave. So far, as far as I know, only one wavelength it will be invisible. So if you put a particular color and go, you will think that you will be, but what happens? Suppose the color is different. You are wearing a red shirt, that color is different, then you will be caught red-handed. So that's the point. Now, so don't think of it. It has not come to that level where you can become yourself invisible and do all mischief. It has not developed to that level. And I think so far something like 15 centimeters or 15 millimeters or something is what scientists were able to make invisible so far. But research is going on in that kind of application. A lot of applications are there. There is a nice novel called H.G. Wells. People of my generation used to read it as an adventure story in the teenagers. And there are some movies with this theme, but they're all horrible movies. They're not nicely made. But the original book is really nice. And this is the invisible man you can make. So what is the use of metamaterials? Suppose a speaker is very boring and he takes too much time. Then you can tell the coordinator, I don't want to see him again. Okay, then he becomes invisible and disappears out of the screen. I said last, but the next last point is we all want everything to happen fast. Everything's going at super speed. I think even my talk is going at a super speed. But why don't slow? What is the light? Light is a maximum speed. Can we slow down light? Can we slow down light? So this Sayana Acharya mentioned, salutations to you who travel 2000 yojanas in half a nimesha, which works out to 2.99 into 10 power 8 meters per second. So the reference is there. I had given the reference where they have analyzed this meaning of it. Okay. So, but carefully I have put the Greek sun god. I didn't want to put the Indian sun god there, but because then I will be attributed to be belonging to some party or something like that. So very carefully I put a Greek sun god as a picture. And the Indian sun god has got 7 horses. Greek sun god has got only 4 horses, but Indian sun god has got 7 horses. Let us give names to the 7 horses. V, I, V, G, Y, O, R are the 7 horses of the sun god. This is, and but if you look at carefully, they are not horses, they are snails. So why? I want to slow down light. How people want to slow down light? Is it possible to slow down light? It is possible if you have a structure. There are many ways of doing it. So one quick way will be you have alternating high and low refractive index. If you have such a material, which Dr. Vijaya will be explaining in the photonic crystals, this is basically a kind of photonic crystal. You can have the omega versus k curve going to 0 slope. And the slope of that is the speed of light. So in principle, you can do it. In practice also, you can do it. So there are several questions that come to your mind. Why should I slow down light? How do I slow down light? What are the principles? What are the techniques? And what do you get out of it? These are the questions in your mind. This is actually a very recent frontier of light. Many of you may be doing research in it if you pursue research career. So I have to answer all these questions, and I have already 1 minute, minus 1 minute. So I am going to answer all this in 2 seconds. All these questions I am going to answer in 2 seconds. What are the questions? What is slow light? how do you slow light? What is the concept theory? What is the experiment to do it? And what do I get if I do that? Read that. That's my solution. We have written it very carefully so that you should be able to understand it. This is available online, free. It is in Resonance magazine. It is the Indian Academy of Sciences magazine, issue on November 2013. Go there and you can search for it. You will get it free. It's a fascinating frontier. I hope that is another take home which I want you to explore. Okay, so I talked about many emerging paradigms, and the other speakers will explain many of these paradigms in more detail, technical detail, and other things. But what is the next paradigm? What is the next paradigm? That is going to be decided by you, those who are going to do research in light matter interaction. I have come to something like the end of my research career, but there are many people, many of you who are starting it. So that is what you people, we have done a lot of research in these things, and this is what you will do, the future researchers will do. I would like to end with a quote from, I think I have been ending like a quitting smoke a cigarette. Somebody said I quit smoking many times. So I am coming to the last topic many times. Okay, the absolutely last topic is, the essence of scientific spirit is to look behind and look beyond. And this is a quote from the lecture which I said. I said there is a lecture by C.V. Raman on why the sky is blue, and hopefully, so I was so fascinated with all that I started writing a book in Malayalam explaining all this in nice language. But the book is something like 90% complete, not yet available. So when it is available, maybe at that time in some lecture I can tell you about that. But the bottom line is, you see a little, and even this little is enough to elevate the human soul and make us realize what a wonderful thing the world is. And that's where I close. So I generally, when scientists give lectures, they talk about some part of their own work. So in this lecture, I have not really explicitly done that. So I thought I will do it in the thank you slide. If you look at this particular paper, that is about an unconventional micro laser, design and development of an unconventional micro laser. And that is our most recent, not most recent, 2020 paper, which came in Advanced Functional Materials. So as a parting take home, you can have a look at that paper. If any of the references which I gave are not available, you can write to me. I may be able to send it. Thank you.